This is a short video about a poster describing our project entitled Values-Guided Agile Robot Research. It is co-authored by Alexandra Gillespie, Nera Trekasemsuk, Reina Hatta, Andrea Giudice, and Stacy A. Dorr at the Department of Computer Science, Colby College, in Waterville, Maine. As agile robots become more accessible, affordable, and practical, research about their potential for applications in public settings are increasing. One such area of research is investigating their use as non-visual navigation guides, where they could serve as a supplement when it is not possible or safe to bring guide dogs. Although the idea of using robots as guides is not new, the commercial availability of these types of robots is making it easier to explore both the engineering and human-robot interaction aspects of this assistive technology. Few of these studies meaningfully include people with lived non-visual navigation experience as members of the research team from the inception of the project. Too often, individuals with disabilities are introduced to an assistive technology solution in the user testing phase, not at the beginning where their informed input and design considerations might radically change the course of the research. In some cases, there are significantly flawed assumptions or engineering traps inherent in the design based on those assumptions. We argue two approaches are required when developing an industrial robot like this as a proof-of-concept assistive navigation aid: co-design principles and value-sensitive design. First, the co-design method of designing technology invites individuals who bring their own lived experience to the design, development, and testing cycles. This framework is closely tied to the disability rights movement philosophy of nothing without us, keeping those the technology is meant to help at the center of research. Our co-designer and co-author Andrea has over 30 years of experience working with guide dogs. She began sharing her knowledge in conversations before we began developing any technology. Next, we moved to in-person observations of her navigating with her current guide dog. During these sessions, we were able to identify critical hand positioning and movements for the development of a handle and harness. We then began iterative design testing in a number of situations, first with in-lab movements, then multi-level indoor settings, and finally, outdoor real-world environments. All design modifications made throughout this process involve direct communication with and contributions from our co-designer. In sessions with Andrea, we learned a number of critical details. First, she shared the basic guide commands for safe navigation for her dog and helped us to adapt them to what she would need from an agile robot serving in a similar role. Andrea also demonstrated handler positioning and essential features of handle and harness, which we used to inform placements that limit interference with Spot's cameras. She explained to us some of the challenges guide dogs face in public settings and helped us to predict some of the same and different challenges that might arise from using an agile robot instead. She also helped us to understand the signals that facilitate public trust of handler-robot teams. For the value-sensitive design portion of development, we had to examine the underlying values and tendencies of groups involved in the development and deployment of our technology. Value-sensitive design uses conceptual, technical, and empirical investigations into values of direct and indirect stakeholders to inform the decisions made as the technology matures. The first component, conceptual investigations, examines the underlying values and priorities of the affected populations, which are distilled into concise design premises related to the technology. Researchers then evaluate the needs of stakeholders who may be impacted by the robot in different campus settings. For our part in this development process, we created an adapted survey regarding attitudes towards agile robots and administered it to members of the campus community. The next component, empirical investigations, tests conceptual premises about which stakeholder groups must be recruited, the level of stakeholder input needed, and the values of each of those groups. In our case, this took the form of 4 focus groups of campus stakeholders with different roles to identify potential conflicts within and between groups. The final component, technical investigations, assesses if technology has aligned with pursuit and sustainability of stakeholder values. This provides insights into the technology rather than the impacted populations. In our research, we conducted user interface and navigation testing with campus community stakeholders and our co-designer. We collected Likert and open response feedback to inform future iterations of these technologies. We learned a number of things from our research thus far. From our focus groups, we learned that trust was attributed to the person handling the robot more than the robot itself. From the survey, we learned that trust associated with the robot had parallel attitudes with the person's attitude towards dogs. Across all modes of data collection, survey, focus groups, and user tests, we found common concerns and potential benefits that community members shared. In future research, a number of steps will be taken. First, we're in the process of recruiting an additional group of BLV co-designers for interviews and input on interface testing with and without robot interactions. We're also working on second generations for the voice app and the handle. The voice app version 2.0 will be powered by phone-processed LLMs. The handle version 2.0 will have a running harness-inspired design with flexible range of motion and enhanced strength. Once we have these new versions, we will repeat co-design sessions and VSD investigations. Thank you for your time and attention. We look forward to sharing future findings from this work as it progresses.